Hey folks, this is Miss Rich coming to you from home. I wanted you to have the opportunity to look back through your notes on double and half angle formulas. And so I'm going to touch on a few things in case you did not get it the first time. If you need to, fast forward to the parts that you need explanation on. And at the end, I'm going to take a few of the problems from your Chapter 5 Worksheet 3 and go through them to see if you need help with that. So first of all, we went through deriving the double angle formulas, sine of 2a, cosine of 2a, and the tangent of 2a. And we talked about how at this level you need to be able to derive formulas, not just memorize them, although we will memorize them as well, and manipulate them so you can always get to them later when you need to. So we derived the sine of 2a by changing it to the sine of a plus a. And we use the addition formula for sine, cosine, plus, remember it's always the same sign, cosine, sine, to turn it into the double angle formula. Sine of 2 sine A cosine A, that's the double angle formula for sine. Same thing for the cosine 2A, we changed it to cosine of A plus A and put it in its addition formula and simplified it to cosine squared minus sine squared. Similar to our Pythagorean identity, but it has a minus in between, which is nice. We'll be able to use that a lot. Now notice there are two other versions. Of course, if we made this sine squared a 1 minus cosine squared, we'd end up with this version. And if we change the cosine squared to a 1 minus sine squared, we'd end up with this version. And you can put those in and try them yourself. But you need to be familiar with all three versions. When do you use which? Well, it kind of depends on what you need. Sometimes it doesn't make a difference. Any of them will work. If you are not sure and you're verifying an identity, sometimes it's better to use this one because it has both terms in it. And then you can always change one to the other. But if you see all sines, for instance, on one side, you'll want to use this one, and all cosines, you want to use this one. So the last one is the tangent double angle formula. We could have also gotten this by putting sine double angle over cosine, because sine over cosine is tangent. But the easiest way to get it is use again the addition formula for tangent, which is tangent plus tangent over 1 minus their product. And we end up with this as our double angle for tangent. So one way that we will be using this is for solving. So if we see that sine of 2x, this could be the sine of 4x, the sine of 8x. We could use this double angle formula in a lot of different ways. The point is, whatever the angle is, if the angle is x, you should have your angle here and here on that double angle formula. But if it's 10x, 2 times 5x, you'd have 5x, and 5x here is your angle. So whatever your angle is what's going to go in this part of the formula. So first we change that double angle formula. Then we see we have a 2 and a cosine in both parts. So I factored out the 2 cosine because of the zero product property. I set both things to 0 and solved, and they're nice unit circle values. Cosine is 0 at pi over 2 and 3 pi over 2, and sine is -1, of course, at 3 pi over 2. So those are our answers. Also, we can use it with our triangles like before. We're given the cosine is 5/13. This right here tells you that the angle A is between 3 pi over 2 and 2 pi, which of course means the fourth quadrant. So I draw my 5, 12, 13 triangle, being careful to make sure that 12 would have to be negative because it's going down the y. And then since I want the sine of 2a, I'm just putting it in the formula. 2 sine A cosine is the formula. The sine of A, I can look over here, is opposite over hypotenuse, -12/13. Cosine of A is 5/13. That was given to us. Notice I'm replacing it for the sine of A and the cosine of A, not for A. The whole function is that 5/13 and that -12/13. And I multiply them together and get that fraction. I've done it also here with the cosine double angle formula and the tangent double angle formula. Make sure when you do the tangent and you have these complex fractions, here I multiplied and got negative 24/5. I went ahead and squared this and then got a common denominator. And then we got this, we can use our sandwich rule, the 24 over the 25, negative 24 over 25 over the middle. And if you leave them as separate factors, you can quickly cancel, so you won't have to multiply. You will not have a calculator on this part. Okay, next page. On 24, we go through, again, a triple angle formula is not ever a formula that you will have to use, but this just shows you, again, how we can derive it by changing to addition, changing the double angle formulas to sine x, cosine x, and the double angle formula for cosine. I actually changed it to the sine version, and then I changed it back to the cosine version, so that just shows you that sometimes you got to think about what exactly you want to get to. It says to give it in terms of sine, but I saw that I had these two cosine squareds and that I could simplify quicker that way. But either way, you're going to get to and here's our final answer. So you can look at that later if you need to. But this is the one I really wanted to get to, changing sine squared and cosine squared into linear expressions. So here, what this is asking is, what is sine squared equal to? And sine squared is not a linear term. We want a linear term, no squareds, no cubes on there, because we're going to have to reduce it in calculus. These are also called power reducing formulas. Make sure you know that as well. So if we want to find sine squared, we can use that cosine double angle formula, which had a sine squared in it, and just subtract our 1, divide by negative 2, and we'll get sine squared equals 1/2, 1 minus cosine 2a. I think if you pick up your pencil and just manipulate that double angle formula, you can see how you'll get this. And the same thing happens for the cosine. The power reducing formula for it is 1/2, 1 plus cosine 2a. Notice it started with a square. It's going to be a version of a double angle formula, so it'd be cosine of 2a. Cosine of 2a on both of them. It's subtraction for sine, addition for cosine. So one of the problems you might see for this is, given a product of two, like sine squared times cosine squared, write those as linear expressions. Write that product as a linear expression. So we change the sine squared to its power reducing formula. Actually, it's over here. And the cosine squared to its power reducing formula. And so they look like they're in linear terms, but we can see when we FOIL them together, we're going to still have a cosine squared, which I go ahead and do here. I've brought those 1/2s together to get 1/4. I did first and last here because they are definitely, that's the difference of two perfect squares, and we got cosine squared of 2a. And so since that is still squared term, I'm going to use the power reducing formula for cosine again. So this is what I was talking about. The power reducing formula for cosine, I got that 1/4 still. I have 1 minus, power reducing formula for cosine is 1/2, 1 plus the cosine of 2 times the angle. But the angle was not a anymore, the angle was 2a. Get all my parentheses in there. So whatever the angle is, you can still put it in the formula, but just make sure it doesn't always have to be x or a. So that will give us the cosine of 4a there. So now we can just distribute that 1/4 through, or that 1/2 through, and we can get this or some version of that. There's no more square terms, so it is now a linear expression. It has been power reduced.